this is covering the topic of IoT. Also, there is a copy of this available, so you should be able to download it, and then you'll have all 57 slides. So what we have here is we're looking at IoT. What is it? What are the levels of IoT? How would you develop different for IoT than for pre-IoT? And then we're going to look at a very formal process that has many benefits. We'll also look at the tools that are needed to guarantee quality, security, and literally guarantee future-proof. And then finally, the last two sections, we'll look at data graph-driven, how data drives everything, not just the car. It even drives disruptions to a lot of previous technologies. And we have a second part of this that will start about a little over an hour after this. And in the second part, we'll continue this discussion as well as looking at how to validate. There's a lot more in the backup. So all the slides, please look at all of them, including the notes. And there's a lot of tips and labs and such. So let's go ahead and jump into IoT. What is it? So IoT is an OT control network, a machine actionable data. The keywords there are control and data. So the control is that it's a system of systems. It's actually sensors and actuators. This is very different from traditional IT because you're actually actuating the motors. You're driving the car, the plane, the medical device. So these are very mission critical oftentimes. It's also connected by internet, the I of IoT. And so in the short term, that's using TCP, IP, DNS, and pre-data protocols. And in the last third, we'll describe how those may get replaced. We're going to also look at functional safety, quality. All these things are under the control, the command and control, even security. And notice how security is different than IoT. IoT is just a surface area. This is actually has an inner ring and actuation. So you have to actually secure all three. So for example, if you get access to a car through any of the 100 sensors, any of the 100 ECUs, you actually have full access to disruptive things. Also the data. The data is the key theme today, and data is what's driving everything, including all business value, not just IoT value. We'll keep stressing going forward, data drives factory, driverless retail, home, everything. And when we describe data, we mean data, metadata, and the semantic domain specific, as well as real world physical specific. So in part one, we're going to look at developing this. And in part two, we'll look at validating this. And I'll use the word quality to mean security, functional safety, quality of service. Quality will mean many things. So in slide 4 here, we want to remind that if we put control in the control plane and all data in the data plane, then the software and hardware layers get much simpler. In fact, we want to get them stateless and under full control so that all control goes out of many traditional places and control can be centralized in one place, more like a telco model. The benefits here are that you get software defined. In this case, software defined all the way to the edge because it's IoT. And you get to program and control any resource, anywhere, anytime. This has benefits of hyperscale because now it's just simply one. There's only one controller, policy, protocol, manager. It's all one. So very simple, very scalable. The data, by putting the data in the data plane, if this is not done, there's inconsistency across applications that have state. They crash holding locks. They crash without transactions rolling forward and back. It's really taking the data and putting it in the data layer. And as simple as that sounds, a lot of software today is still having a range of quality about the data when they should just have a middleware layer to push all their data to. And footnote 2 there is especially important because there's 3 excellent IEEE papers describing how to make thin software by having thin apps, APIs, and management, and pushing all the data to the data layer. Doing this with hardware is very similar. Doing this with Microsoft OData is similar. So if data is so important, then what are the levels of maturity of data? And we're going to describe multiple levels here, phases, if you will, and customers can decide, and developers need to target these customers. So it's really how future-proof do customers want to invest. At a phase 0, that's the old embedded generation. It's not even connected to internet. Phase 1 does add internet. And in fact, if you look on the far right, there is a smart parking example about these generations. So pre-internet in the lower right, that can only tell you if the smart parking spot is empty or full, 0 or 1. That's all you know. As soon as you add internet, you can now tell all the empty spots, where they're full, the history. You get a lot more information when you start having data times data there. Now in phase 2, it's not just IT and internet, but it's actually the OT control network. And this is semantic meaning. When you get up to this level, it's much more powerful. You can start to ask bigger questions like who, what, when, where. You start to tie to the physical world. You now have a digital twin to the physical world. So your data is much more valuable. Then after that, the data starts getting a common format. You can correlate the data, the artificial intelligence and learning on the data. So now your data can be sold and interchanged and work with others' data because it's correlated to work with everyone's data. And then work with big data and continually learn. Similar to this, the control plane is correlated for things like software defined. So now everything's are under contract, centralized, rule of law, work with others. And this is the best state of the art today. To get to this maturity level allows the highest value of your data. And as each phase, you get to mature your data for more and more value. Data is all business value. IoT data is all business value. A coming phase here is when the artificial intelligence can adapt and abstractly learn more like human intelligence. And when data graphs replace internet, computing, human contracts, and much more that we'll describe later. So it says at the bottom here, what's the right level of investment for your IoT projects and sub-projects? Is it phase 2 and there's just limited benefit, or do you want to invest enough for future-proof phase 3 and even start preparing for AI and data-driven phase 4? Notice again that it's all about the data, and all value is the data owners. Who owns the machine actionable data, like that smart parking example on the right? So this is the background to get us to development. With this understanding of the importance of data in IoT, then the question is, how is development different? 10 million developers out there. How would they be different for IoT than for traditional IT and web development? And you can put in the left column, most of the 10 million developers are going to be like a web developer, JavaScript, or say an IT phone developer in Java, whatever. And so you get the idea of the two columns here. But notice how different it is. Like in the very first row, traditional development is more like an art. It can't double requirements every year. It can ensure that that car is regulatory compliant, that driverless is safe. It can ensure that an error can never happen again. That's really an informal art. On the right column is formal math that is complete, correct, future-proof, and is sufficient for driverless factories and everything else. So there's many examples of that. For example, Internet Row. IETF only created the syntax. That's it. There was no version-specific integration. There was no semantic, no metadata. So it's very limited. It'd be like saying, here's the parts store to a car. That's very different than saying the car can have semantic meaning for smart parking, lane keeping, smart braking. See, the left column is more like just the parts store for the car, and you can plug them together with an API. That's all internet is. That's all IETF provides. So things, the best case for things is the 3 nines uptime, 99.9% uptime. That's 51 minutes a year of outages. Not what you want in aerospace, medical, and other major fields. Security. There's a lacking of functional safety because it's not tied to the physical world. There's not a concept of digital twin. So if we go back to our original definition of IoT as an OT control network of machine actionable data, how do you guarantee control that you brake in time, airbag in time? How do you guarantee that the data is machine actionable, including security? So those are the things we're seeing in these rows. If I jump down to the blue rows at the bottom, development, which is this presentation, is today, state of the art is mostly like paper. The requirements, the artifacts, the deliverables are manually aligned together. There's not a single model, single system of record for developers. For the entire life cycle, all users, all views, all reports, it doesn't even auto-generate the code and test. So how can you know that your code and your unit tests are going to be compliant? That's very, very important. If you're not regulatory compliant, how can you sell into most of the IoT market, most of the high margin market? And then the second presentation at the very bottom, which we'll touch on in the next slide, is how do we validate this? There's some APIs in traditional development that say, yes, I can put them together, but there's no math guarantees. There's nothing that says that I can complete and correct know how formal this is. Think of the entire left stack there as an informal art. If I stack 50 Amish barns together, that's not a skyscraper. That's an art. I respect art, but it's not the same as saying, I want to keep doubling, twice as many skyscrapers, twice as high, twice the wind, twice the weight. That kind of formal CAD and engineering is the right column. Very different. So what's our motivation here for validation and development? This is a common model used, the V model, where on the left, you'll see that you start on the top left with requirements, you come down through design, and then you start getting the software, and then the components, and then you develop. So down the left, you build it, and up to the right, you do the testing for this. And so this is very typical of development today. But what you'll notice are the numbers from a very large government study by NIST.gov. In blue there, 70% of bugs are introduced in the early phase. Only 3.5% of these faults are discovered. And if you think of removing them as a unit of one, notice the red in the later phases, how much more expensive it is to remove it. So the whole theme of my presentation here in part 1 and part 2 is it's very cheap to avoid, find, and remove the faults early. It's very expensive to remove them later. So the problem here is this 3.5%. That's the whole problem of IoT quality, of all IoT development. How do we get that number to 80% and keep increasing it? How do we make sure that all departments, all companies you partner with, have it at 80% or more? You could build a car and every $1 part in there could affect the quality. Same thing with aerospace. How do you make sure how formally complete and correct and how early they can catch these faults? This is how you develop for most of the money in IoT, most of the value. So notice in the lower right, expect IoT to increase these costs by about 100x, because now you're talking medical, aerospace, and it's a digital twin of a very changing physical world. very changing geo, country, regulatory, a lot more change than usual. So it's very expensive. Another key thing about the formalism we're going to talk about today is the goal of continually doubling requirements and also ensuring that you cannot reintroduce a fixed problem. If you fixed an error, it cannot be reintroduced. So that was the introduction. Now we're going to look at model-based and the process, and I'll call this the long-term how. We just looked at the short-term what. Now we're going to look at the long-term how. How do you build it? How do you develop? So the key here, it's one formal system of record. It assures everything and generates every view. The assurances are things like reports to say we guarantee we're regulatory compliant. We guarantee this is the optimal schedule for development. Here's the executive report. Those are the kind of outputs that you can assure. And then generate the APIs, the unit tests, all from one source, one system of record. Now, there'll be other system of records, but those are secondary to this. So this could feed something like DOORS, which is a well-known requirements tool. It could feed all of the major other system of records. So we're really describing one global model. We're also going to touch on a language, a modeling language, ML modeling language, and system modeling language is what we'll be talking about quite a bit. And you can look at it like it's blocks, it's flows in green, it's also parametrics and requirements in red. So it's really got three parts to it that we'll describe a lot. Also, this one view can be viewed as one mountain. There'll be lots of reports, lots of views, but those are like taking pictures. And any view of it is going to quickly be incomplete and quickly outdated. But the mountain is always correct, and it's a single system of record. That's key to all model-based software engineering. So formal model-based software engineering is one process, one language, and one tool that implements this language. Why this process? Why this language? That's our next topic here. So again, model-based, single mountain, single source. How do we get all inputs, the earliest possible requirements, detect all faults, initially at least 80%? And without doing this, the explosion in complexity of IoT will affect late debugging and testing and quality. Just vulnerabilities, security vulnerabilities alone. Whereas this process we described today, you cannot add a new error. You can also know who broke the build. At check-in, you will know who broke your hardware, who broke your software. So we'll describe the object-oriented analysis design methodology, and SysML is the language that we're using, and then we'll cover a few tools to support that. So if you think of this end-to-end, this is the far left is the inputs, and those are really the requirements and key performance indicators. And sometimes I'll call those parametric constraints, but key performance indicators. And then the layers of the solution. What are the actual layers of your middleware, your data, your network, your platform? And the data is really key. Data drives everything in IoT. Your ports. A key concept in SysML is to connect these ports. That's where the complete and correct comes from for developers. And we'll describe how those work. And then the output is to generate these assurances of quality, and then also auto-generate the initial code. These are the initial hardware interfaces. These are the initial software interfaces. Those get auto-generated from this language and from these tools. And if you start with quality and keep guiding every build, every check-in in your version control, you get to keep ensuring that there's no port conflicts, that end-to-end, every block, every flow stays complete and correct. You never break your low latency performance, your encryption requiring 512 bits, Every attribute you require is enforced with every check-in. Reports are always evergreen. You always know where you are as far as the full compliance, where you're out of compliance, and where you haven't even started for compliance. So model-based systems engineering, this came from the INCOSE book that I showed in the previous slide, but that is paper. So that's actually here in the left column. It's a manual document. So when you talk about software engineering, the left column is traditional many disjoint systems, much paper, trying to keep those aligned, whereas the right column is formal, one system, and you can exchange it over XML. So the XMI is the XML interchange, and it guarantees to work with other tools. So the right column is one model, one formal. Oops, let me get that off the screen. I apologize. And down at the bottom, you'll see that model-based is really one process, one language, one tool. And today we're going to use Spark Systems. And anytime I use an asterisk there, that means it's we want to respect others' trademarks. So part one is how to develop it. Part two is validating it, and what are some best practices and tips there. So hopefully you're going to hear a lot of best practices and tips today. So model-based system engineering. Here is a typical cost scenario. And this is based on University of Southern Cal, Dr. Barry Bohm, and it is huge studies there. And if you notice to the far right, number 2, that would be a very heavy process, and so the cost might be $1,000 per line of code to develop. NASA is in this category, and there's others that have justification for extreme over-engineering. Even complex UML that's now probably more like 40 diagrams, the full INCOSE paper process. Without an automating tool, these get to be very heavy and very expensive. Even more expensive is agile processing, like number 1 there. That if you have a very quick method that cannot fully and completely verify on every check-in, did you break the hardware build? Did you break the software build? Can you guarantee this is functionally safe? The properties of this airbag, brakes, steering, what can you guarantee about it across 10 radar systems and 100 small chips? So that is under-engineered, which is the most expensive. Now, model-based, on the other hand, we'll describe more detail there. Not only is it the best ratio for cost, but it keeps scaling, as that dark arrow shows at the bottom. Now, you can still use an agile style, and you can still do sprints, but it would be using the SysML and the model-based, such as a weekly check-in, and then, at worst case, is a weekly is the unit you're willing to risk. So what is SysML? That's, this is very important to today. And think of SysML as 7 diagrams, 4 that are like UML, 3 that's slightly changed. Then it adds 2 more diagrams, requirements and parametrics, that I also called key performance indicators. The power of this modeling language is that you can add these in place, and you can chain them together to guarantee this property. So if you have something like this airbag must go off and with this latency, these brakes must respond this quickly. If you want end-to-end requirements that are time, space, security encryption, many others like that, then you can do the ports to connect them, and you can actually put these requirements and KPIs, and those are the blue dotted lines, the requirements and parametric KPI. Those are actually have the dotted blue around them because they can attach to anything. And in fact, they can even attach to subblocks and subflows. And as you model things and build up models, you only have to build them once. Then you can keep improving them. So when you build a model of a middleware an OS, as you build this up and keep improving it, then you get to actually model and validate the machine actionable data and how it's controlled, and to have these assurances as early as possible. That's the whole key here, is to remove the faults as early as possible before they cost you 100 times as much money and time. So why SysML? On the right side, you'll see that it's the clean subset of UML. UML is not orthogonal. There's 2 or 3 ways to do many things. In SysML, there's only one way to do anything. The second point here is the attaching, to actually get these requirements and KPI per subblock and subflow. You get as granular as you want to get, and you can chain these together. Another key value that UML doesn't have is that you can model hardware. So you're really modeling all software, all hardware, the entire solution. UML only gives you data types. This gives you value types of physical, real world, and mapping your digital twin to the real world. It's also well aligned with IoT, conferences, standards, any place you're going to see a lot of SysML. You're not going to see much UML. And then finally, the model-based languages, if it's any other style of languages, it can't represent systems engineering, or it's not a fit to IoT. So this is a very clean, useful language for modeling IoT. The history of SysML, as this shows briefly, is many object languages and object models got started, then eventually got unified into UML, the Unified Model Language. The challenge there is when you put that many things together, it's hard to be orthogonal, cleanly separate as you put together the union and not necessarily the clean isolation such as orthogonal. The other difference here, and UML2 improved that quite a bit. Another difference here is using the INCOSE, because that is the definition of systems engineering to government and many others. And so to import INCOSE, the paper version, and UML2, the same subset of that, now creates SysML. So if somebody wanted to develop SysML soon, what they could do is get a commercial product or a free open source. So here's the product that I'm using in today's overview. And you really want the current version of SysML. You want ports. You want to be able to export to the major programming languages. You also want to be able to do XML interchange to open source and others. Now notice here, you want to avoid diagramming tools. Those are not SysML language tools. There's no language, there's no model. It's just, you're just dragging documents on the screen. There's no underlying math for complete correct to build an IoT. And then for open source, Model.io is very impressive. So it's surprisingly good, and you can also import, export to the commercial products. Other open source may not be as good a fit to SysML unless they have much more maturity in the diagramming and underlying assurances. A tip here is to make sure that you can import, export with open source. Another tip here is if you get one of these, highly recommend the floating licenses. And 10 floating licenses may be enough for 10 senior architects and developers. We looked at how, now we're going to look specifically at the hub here. What are these inputs and outputs? So here's the diagram we showed earlier. And the key here was that you've got multiple inputs, and then you've got ports to guarantee the complete and correct, and then you have the different outputs. On the input side, data is well known, but we're also stressing to get semantics and smart contracts. So a key here, and I've got related IEEE papers on this and many other things out there you can find under my name, but the key here is that it's not just isolated data, but you actually tie things to it. So you take, for example, data, which is naturally a low-level layer, And then you put a very high-level semantic layer like OWL description language, and a high-level thing like smart contract clauses. And notice this skips all the layers in between. So by picking a low level, such as DDS, that's very secure, and DDS, there's no single point of failure. There's no in the clear text. There's many other things that a lot of other transports lack. So, and then OWL-DL that was actually based on the DARPA agent. So again, very secure. By combining these two endpoints, it skips a lot of layers in the middle. It also provides data quality, data checkpoint, data driven. And so what feeds our SysML is heavily data, and then coupling that with semantic and contract guarantees. On the output side, assurances, as we mentioned, multiple kinds of reports, especially that it's executive decisions. At any point, they can know the exact status, schedules, and then compliance, know how close are you to compliance? How could you quickly extend the one model to be able to sell into another geography, another vertical market, to do more granular functional safety or quality, to do stronger encryption. Aerospace wants 512-bit encryption. How do you guarantee that as early as possible in all your designs? Was that ever broken in the design? How could you know that in 5 minutes? Checkpoints. To checkpoint the data action, all data transactions, all machine-to-machine contracts. So these smart contracts and payments between machines. How do you checkpoint and model those in your development? And then to auto-generate the start of your software and hardware. So we described assurances. What is an assurance? Think of this as a quantitative metric. You now know the level of confidence and validation to back up your claim. And this claim is on an architecture that continually changes. So this is assurances on models that map to real world. This is a high-def map of a car in its situational awareness and its target mission of where it's going. Same thing with a drone. Same thing with many other IoT devices out there. So an assurance case is real evidence that shows real artifacts that have real properties. It's a chain that's driven by key performance indicators, and we're going to describe data graphs here in a minute that even improve those further. And then how you do that is with SysML ports that document these properties and keep them. We can also export and run it on the simulator. So things like Simic Simulator, your software is guaranteed to run as is in production. So if you simulate and build up, say, an entire data center, and then you want to test that on your laptop on a workstation, really stress it if you want on a cluster, but to develop to that with greatly improves and allows all the hardware, software, and integration testing very early on, before you build the entire data center. So this allows co-design. It actually runs your software unchanged in production, and it's formally complete and correct. So here's an example where a simulation was built up that is workstations, clusters. You can just build up an entire data center, build up a factory. And so, you take the controllers there, you build up a board, you build up, desktop servers. You want to model an entire fog for IoT, an entire assembly line, but you build that up and then test it on your laptop. So we've looked at how to develop for long-term, what's the right model, language, tool, and we have much more on language and tool and backup to show you. And we also want to touch on data graph driven. So on the agenda here, think of this as the long-term what. So we initially showed what IoT is, but in the current generation of IoT, a lot of things have limited data. If data is driving the car and the factory and automating all IoT, then how do we set data free? What's limiting data from being the only driver, the only first-class citizen? What are the limits to data? And it's surprising historically what tight coupling we've done that affects development to be future-proof, data-driven. So what limits data? If you took a snapshot today, you would see that routing is not tied to the data. It's tied to many IP addresses, many protocols. Naming is tied to IP addresses. Certificates are tied to files, blobs, not the data owner, not any data requirements about IoT's quality. What parts of IoT need low latency? What parts need to be mission critical, massive dense, smart, mobile? There's no isolation of data or its quality. Data's driving, but it's not first class. Also, there's no boundaries. How do you get to fault tolerance boundaries of data if today the boundaries are pretty artificial software, hardware blobs? And in fact, you will rarely see more than 99.9% upside outside of Erlang OTP. Outside of Telcom developed protocols, you'll see almost no fault tolerant 9.9s. Today's execution and computing, that's tied to an entire core, or even so your data has to hop all over that core, moving over what's known as dark spaces, huge 10 nanometer spaces of transistors, because the data has to keep moving. And that affects all power, latency. That is now your surface area and your boundary for security, fault tolerance. Every time you move the data, it affects all of these. Data movement equals the cost of power, latency, and the boundary area for security. Artificial intelligence wave 2 is very fragile. If you learn and then send those learnings to the car to drive, and then you change severe weather, you change any context like drive in the left lane, change the mission, and the entire AI learning is fragile and worthless. Contracts. How do you do contracts that are still human and not data-driven? Human cause misunderstandings, litigation, that you can't compose them together. You can't just connect contracts together. They're human. So everything here is not composable. It can't keep doubling. You can't formalize. So now we're going to look at data. So here on the left are some of the ones I just described. And here's the data graph-driven disruption. Here's the semantic benefits to developers to develop to this. And here's the leading examples in the far right. So because today's talk was future-proof, we really want to stress the future-proof of what are we developing to. So be aware, for example, that first row is when you're developing mission-critical, how do you make sure you know your data boundaries? Your data dependencies, because that's the only way long-term we're going to get out of shared models that are only 3 nines upside. The best you can get, as soon as you share memory or have a shareable language like Java, the best you can get is 3 nines. TCP/IP, Internet version 1 today does not treat data as a first-class citizen. On the far right, if you go look at the IEEE articles, the IETF.org, the start of protocols around named data networks, you'll see the disruption coming to replace TCP/IP. There where you have mission critical, massive, and high quality data, you're very advantaged using NDN over current internet, over current DNS name services, over current 509 certificates. And all those articles you'll see searching on those terms in the far right. Computing. Computers as we know them send data across the entire core. And the generations of computer are tied to how far we move the data. How do we mathematically guarantee that we are moving the data the minimum distance to get massive performance increase as well as quality? And then on the AI, how do we use that kind of hardware under the AI, as well as use that domain-specific data-driven neurons to drive a new generation of AI? So in short, at the bottom is remove everything that limits data from being the only citizen. Complete freedom. If data is going to drive everything, why do we artificially tightly couple all these things around it? So more examples are DNS naming, data packets, and smart contracts. We'll touch on these. So here's one that we mentioned before, is that the data dependency graph is the ideal isolation for semantics and quality. So here is an OTP example where a developer has to realize all dependencies, the ideal level are these arrows. So if worker 3 process has a fault, it affects worker 4's dependency with the blue arrow. In fact, it has 2 data dependencies here. And so both of those will live and die together. And their supervisor process will detect a fault in worker 3 and restart both. And restart should be sub-second. That's how telco works. And so a supervisor has very lightweight restart, very stateless, and spawn, migrate, copy in guaranteed quality time. This is how all telco quality works. And the chain of supervisors here is key. So this principle of data dependency graph, that's what drives everything. Here it drives isolation levels, fault tolerance, quality, security, many of the non-functional requirements. Why do we need this? I mentioned uptime. Errors is another one. Current data code is an error every 300 lines. That's current error rates of higher quality. Current code is not transparent. Unlike OTP, current code, you have to code per platform, per network. There's no referential transparency where the output is the same as the function. There's side effects. So this guarantees transparency, referential, per node, per network. It also scales. You know, how do you have much lighter weight processes, very brief very brief impact to the data so that it scales, many more per platform. Same thing with concurrency. So these are just some of the conditions, and this is why you can't use traditional languages, shared memory, and shared processes, and shared models and techniques, threading, locking. All of these can't beat 3 nines. So I mentioned named data networks. On the left is your traditional TCP/IP. On the right is named data networks. As I mentioned, how do we get the earliest data, capture it, package it, right off the sensor? Name it, own it, control it, publish it, subscribe to it. Notice how different this is than creating IP addresses for pieces, parts, and not knowing who can see what. Not knowing what routing, what dependency. How do you mux and traffic this? You know, in the left column, how does anything work? It's quite challenging when data is not a first-class citizen. And now that we have, remember the definition of IoT, we now have an OT control network of machine actionable data. How can you control it? What do you control? What's actionable? Data has to be first class, even with the naming. So CPU. You can think of CPU microarchitecture in 4 generations because it's really about the speed of light. If you can increase the density and get them smaller and smaller, you can keep doubling the speed. Clearly, you can't improve the speed of light, but you can make it half the distance. So, number 1 here, that generation was the entire die. The data had to move across the entire die. The second disruption was to have many cores. So in a 10 by 10 area, you're now down to 0.1 times 0.1, a much smaller area for the data to move. Remember, data movement affects all latency, power, all surface area, boundary for security and quality. It affects a lot of things here. So the third generation of microarchitecture is HSA. That big cores with extremely small cores, even things like TensorFlow cores. So very simple transistors. So in those cases, you get data algorithms to map to the simplest transistor type possible, the highest density possible. So if I'm only doing matrix operations, I'll put it on a TPU core, and that'll be much smaller, much tighter than a much larger core like GPU or FPGA. So these are the techniques in the third generation. The fourth generation, this mathematically guarantees the minimum data movement. So through approximation algorithm to guarantee that your data is on it's been overlaid to the smallest area possible. The ideal boundary to secure, to guarantee quality, to have lowest latency and power. So those are the 4 generations of microarchitecture. Again, data graph driven. AI being data graph driven. At the bottom link there, you'll see that government funding is tied around 3 generations of AI. The first generation is what's called descriptive. So products out there, Movidia, Saffron, IBM Watson. So these kind of products are tied to cognitive. So cognitive is really just the as is. So cognitive is taking the as is and creating a dictionary of relationships of everything in the as is. So it can describe what's already there. It can't discover and predict new. So for a lot of solutions out there, it's nice to know the optimal. It's nice to know relations you don't have. And so there's a lot of solutions to wave 1. Still a lot of artificial intelligence to be gained from that. Wave 2 takes it a step further by being able to predict. Now you're getting into a should be model in addition to the as is, and to predict never before seen how should a car respond to a new kind of safety sign, to a new barrier, a new obstacle, a new weather. How can it predict? How can it handle big data far beyond what a human can handle? See, wave 1 was just rules. Wave 2, and then 2B, you can actually start adding optimization. Then you can start predicting, beyond prediction, and prescribe, because you statistically know this part's going to fault soon. You can actually do maintenance early. So those are the first 2 waves. There's a coming wave 3, and clearly wave 3 is going to, it's very, very early, and we're probably several Nobel Prizes from realizing that more human-like intelligence there, ultimately having to be very data neuron driven on very data graph driven hardware and memory to keep scaling. So this also affects AI. On the second example, I mentioned data plane kit and how developing to this, this is first class data packets, no interrupts, no blocking, no copying, no ring transfers. It's more like direct memory access. This is used by all major data packets. So if data is going to be a first-class citizen, how do we not create interrupts, blocking, synchronous, and other limits like on the left side? And this is with off-the-shelf hardware. So all IoT gateways, all major switches use this on off-the-shelf hardware. So we have 7 minutes left. I will touch on just a couple of things just to show you where I'm headed for the second hour. We'll look at modeling from one architecture. We'll look at aspect-oriented, how that treats the data first class and does not have some of the limits of object-oriented. A single model to do all validation. We'll look at stressing our solution by having God mode and an adversarial red deity stress test. If we say we have autonomic IoT solutions, how do we stress test them? And then we'll do a call to action about how do we develop with SysML, have mentors, and how do we measure architects and developers based on how much they deliver, not how much gets thrown away. What can keep doubling? What is formally correct and complete? And then how does this become our only system of record? Where can I get more information? Lots of useful links. There's a great book on SysML there. And then if you want to get 500 slides, it's a tutorial to go with that. There's the link. If you want a free ebook that's only 70 pages that shows how to generate your software APIs and your hardware APIs. So it builds a working prototype of an IoT device using the process, architecture, and language we showed today, all in one book. Where can you download more information? I think what's also important here is these are videos that you can learn from. There's the open source. Here's all the acronyms you saw today. So a lot of acronyms that can save you time. And in backup, how do I learn quickly? How can I download a trial version and use it for 30 days? How can I extend it and use it for 30 more days? How do I make sure I'm using the version that has SysML? What's the process for some early learning of SysML? How do I do like an RSVP and build requirements, then structure, then variable behavior, then parametrics? What are some labs I could build and how would I build them? What's the use case? So these are, how can I get certified for all this? Then there's the normal legal boilerplate. So let me go back here to the call of action. More information. So highly recommend this process. And here's where you can get a lot more information. So if you have any follow-up, you should have the my name there and email. And we're obviously very glad to help and very excited about the possibility of future-proof IoT development and validation to develop once and to continually double the requirements. That's engineering. That's not an art, that's engineering. Keep doubling requirements. Guarantee that you can never make the same safety mistake twice. So we're back to the slides here and where you can download the slides and you should be able to access all 57 slides to both presentations today. I also have the link copied at the top of the screen. So let me do a brief review of what folks saw the first half. The key here is that what is IoT? How is it different for developers? What's a process that you can use long term? And then what is going to be replacing a lot of IoT as we know it? And those are the key themes in green there. We'll emphasize the validating and how to actually set up a dev environment for this. So what is IoT? Although we covered this in the first hour, I just want to remind folks, IoT is an OT control network of machine actionable data. It's about the control plane and the data plane. Those are the two layers that have really changed. Control is not like an IT, just read access, but this is actually write access. It's the actuators, the sensors. So it truly is a system of systems that gets control. It includes functional safety and quality of service, things that were not important when you had read access to a human in a browser. Also includes security that got added to traditional IoT surface area because OT added an inner network and actuation. So take a car, for example, is not only do you have to secure the surface area, but once you get access to what all the chips, about 100 ECUs, embedded control units, about 10 different radar systems, when you get access to that inner network, you've really compromised and you can start actuating. So very different security needs. Data is also different because ultimately data is what's now driving the driverless, the factory, and everything else. So all business value, not just IoT value, but all business value is this disruption of data driving and making that work with Semantic. When we say data control, we really mean how do you put all the data in the data layer, all the control in the control layer. This lets software and hardware layers be very thin. By doing this, you get many benefits, much like software defined, where when you put all the control together, you can program any resource, anywhere, anytime, and you can keep scaling the benefits, the functionality, the value, with the simplicity of one controller, one policy, one protocol. It's really simple. And if you're following along here on slide 4, similar benefits with data. If data is the only layer with data, apps and hardware can be very thin, very stateless, and easily controlled. And in fact, you can even get the hardware software semantics with software defined. This data layer, if it's missing, then apps are basically doing data's job with a range of quality. Some apps will crash holding locks, won't have transactions to roll forward, roll back. So a lot of problems in quality in the IoT space if you don't emphasize the two layers that matter, the data layer and the control layer. And everything about development and validation emphasizes those two layers. The paper at the bottom here, IEEE paper, get that to understand the value of these thin layers. Similar techniques are done by Microsoft OData, and similar techniques can work with hardware. Here's the generations of IoT that we covered in the first hour. This is probably the most important to understand the difference. The left column is traditional pre-IoT, more of an art. There's no way you can double requirements every year. You can't ensure that an error can't come back. The left column is not adequate for things like driverless car, aerospace, medical, mission critical, smarter semantics. Only the right column is formal, is true engineering and not just art, to guarantee complete and correct. So there's other differences here in the multiple rows here that show pre-IoT, but the biggest difference here is the development itself in blue at the bottom. That in the past, where there really was no evidence of quality, there was no auto generation, there was no formalism. On the right, a single model generates everything, so as early as possible you know the faults and problems and can continually integrate everything to one model. Same is true in validation that we're looking at now. The bottom row in blue there is that in pre-IoT, it was very informal. There was no sense of what was the amount accomplished. There was no assurance of quality, no regulatory compliance. The very next check-in could break a major feature like latency for an airbag or brakes? And how do you know those things going forward? So here's the motivation for why everything is model-based system engineering, MBSE, is that to validate on the right half here is impacted by the earliest possible fault detection and removal on the left half. And statistically, this is one of the biggest studies done by NIST.gov, is that 70% of the errors are introduced in blue there on the left. Only 3.5% are discovered. And if the cost is considered 1x, it's much more expensive than later to remove these. That is the problem of IoT development and validation. It's cheap to detect and remove early, which is this process today. It's expensive to try to detect and remove later and automate that. It gets better in that we can continually double the requirements and scale. We can also ensure that an error does not get reintroduced again. In the lower right, notice that this diagram was pre-IoT. So with IoT, you can expect these costs to be about 100 times more. You're not just faulting the software, you're faulting a medical device, an airplane. And so to actually guarantee and triply redundant and other improvements to comply with regulatory mission critical, even to be the digital twin of a very changing physical world, all of those mean that these costs on the right in red are much, much higher now. So the takeaway here is this is our motivation slide, why we develop for quality, entire life cycle, and validation. Guaranteeing complete and correct. So here's how to do it. It's one process, one language, one tool. And this is the long-term how. And you develop and design for validation. It all comes from one model. One set of structure blocks, one set of behavioral flows, and then attaching parametric and requirements to those. And by having that one united source, it keeps everything current and complete. And from that, you can generate assurances and the initial code and all initial products and views. So two separate things. From one record, one system of record, you generate all assurances and you generate views. And we'll look at each of those. We covered this earlier. So we'll cover, we'll jump down to the later version of this. This is good. Okay, so here is input. The ports in SysML is what give it the complete and correct. So inputs here, you expect all the layers. So to really validate this, you need to know all platform, network, everything that you're coding to that can affect your non-functional abilities. Also the requirements and parametric key performance indicators to get these from the different vertical customers and end users, put that in the ports, attach it to the ports, and then document the assurances and the initial code and unit tests. This is a huge automation and improvement in quality over traditional development. There's much more detail in the slide notes if people need it. Also, there's complete acronym list in the backup slides because this is going to have a lot of acronyms here in this second hour. So when we think of inputting, part of those inputs are going to be, every form of data, because data is our primary concern, and that's why it's the thickest lines there. If we manage the data well and control it, then everything else can be very loosely coupled, removed, fixed, with much less impact. Same thing on the right. If our assurances are strong, so that the thick bold lines, everything that we know that we're regulatory compliant, functionally safe, if we can document those assurances from the SysML, then the other outputs from this are secondary. They can do one-time code generation and other one-time things, but it's really about the complete and correct and reporting on that. So what are assurances and how does this help to validate? We saw that assurances here are levels of reporting, and you can report completeness level, detailed status, even schedules and development schedules and estimated approximations of how long things could take, how complex something is. You have some really interesting opportunities here that we'll detail later. Also to show compliance and to know even size, how big it might be to build a new product or to move into another geography, government, or regulatory area. How many libraries do you already have? How much functionality do you have to modify your IoT solution to go into another space? Very useful for a development team to know. And to know your checkpoints of what data actions and transactions, and those are going to be critical since data is driving, and to have all of your machine-to-machine guarantees. And as we move forward into newer phases of IoT and have more and more machine-to-machine traffic, including contracts and payment. So it's heavily about the assurances as well as the auto-generated. So what is an assurance? An assurance is quantitative, and it gives you a metric of confidence. This way you know that your validation tests verify your quality. The challenge here is that IoT continually changes. It is a digital twin of the real world, of the physical world. There's also more and more features, granularity, and opportunity to monetize. And so with this much dynamic nature, assurances are needed to know that something is regulatory compliant and such. And so to build up your assurance cases, it shows here in the middle, there's evidence that has convincing argument that shows the properties of artifacts. And I describe how this is done in the modeling language of SysML. We skip the portions that show why did we pick SysML. That was shown in the first hour, but we will give some examples of validation as well as how to learn SysML. So to validate, one output of this end-to-end validation technique is to output to actually run on a simulator. And the benefit here is that you can model the entire data center on your laptop. So Sniper is an open source version of this. Symix from Wind River is another. But to be able to actually validate and test and run your entire solution so that your team is always in sync co-designing. So you're not waiting for hardware, software. You put up the existing API and you keep going with your solution. As an example for IoT, the next slide shows you can build up everything and validate early. So you can develop and validate at the same time. So we just showed at a high level what is the unique development needed for IoT. How's it different? What is a long-term software engineering that's formal? The process, the language, the tool. And we covered that even more in the first hour. And now we're getting into long-term replacements. That if data is driving the car, data ultimately is going to influence, change, and replace a lot of technologies as we know it. So there's many things limiting data today that were historically randomly put together. Why do we tie IP addresses to non-data? Certificates, naming, all that to non-data? Why wouldn't data be the first thing captured, packaged, secured, owned, managed. Why do we have these many other things here? Even execution there, where data has to travel all over a processor, instead of guaranteeing the data is at the minimum area. Moving data affects latency, power, quality. Now an entire surface area of where the data was is impacted for things like security and reliability. If that's a very small area, that makes security reliability much more granular. So here's 4 of the many benefits when data graph is driving and replacing non-data legacy. So the first example we'll cover in the next slide. The second row here is that there are techniques now to replace TCP/IP, to replace typical compute, and such. Also, naming schemes that are much more secure and much more data-oriented. Techniques for data on platforms that will scale platforms 2 to 50 times. And even techniques for data being the first-class citizen of contracts. So here's the first example in more detail. That when data is the isolation level and data dependencies, that is the ideal level for meaning and for highest quality. And when we say quality here, we always mean security, functional safety, quality of service, fault tolerance, all of the qualities we kind of bucket under the word quality. So in this example, the worker 4 is dependent on worker 3 with 2 data types shown by the blue arrow. So if worker 3 has a fault, it impacts worker 4, and both of them must crash and be restarted together, hopefully in sub-second. This is common in OTP telco. And this hierarchy of supervisors and this technique of rapid restart around data dependency takes telcos to 9 nines reliability. The best data center is only 3 nines, 99.9%, because they share memory, share language. A lot of resources are shared. Here, this is data specific isolation. The ideal level, therefore, the ideal reliability. So we got to more details on quality and what makes it high quality. And then we're getting into validation. So how do we validate what we've seen so far? So this is the emphasis of this second hour. And we point out that there's only one architecture model. When you're doing SysML, there's one authoritative, one version. So if you say this is your IoT gateway, fog appliance, thing, there's one model. And then off of that, all of those port annotations can be per category. So for example, the bottom one there, timing. All latency, scheduling, coordination, synchronicity, all that, you can analyze that off of the connected ports of the SysML. That's huge in that you can know in advance as early as possible were the requirements met, were the key performance indicators met, and you can know any changes at all to the design, who broke the bill, who no longer keeps the timing constraints for latency. The airbag won't go off in time. The brakes, the lane keeping, you're no longer meeting the timing requirements. That's why it's so important here to be able to have a single source and to validate off of that as early as possible. It's very low cost to add these. Once you have your model, you can add any dimension and do that non-functional annotation off of it per space, time, identity, all the faults. And that's what the examples here show. In the short term, validation is around objects, and that's the process. I do want to point out that at some point, Validation may be around aspect oriented, so that you can do any data property, anywhere, anytime. Still data driven, the key is the data. Notice here that in the left column, object oriented is only static compile time, only has 3 properties between classes, and only static classes, not runtime. And the scope is only parent-child. That's it, only hierarchies. Aspect-oriented is a vast superset of any dynamic time, any relation on both the static classes and the runtime instances, and any data scope anywhere. So the right column is really the sufficient superset of object-oriented. And if you use SysML ports, ultimately the right columns are the connection types between objects. It's the junction between any 2 classes that you can develop to, debug, validate, and that's where all the assurances come from. So you generate SysML ports, and we'll describe how to do that, and then you report on that for all reports and for all runtime connections. And if you have any questions, please post them to the window. So this single model validation, think of it as there's only one model, and you can do all this reporting per dimension. If you want just security or just the resource consumption, what has low latency? Each one of these dimensions you can report on. You can also start doing predictive and have insights there in the model as well as in production. The key at the bottom is that with one source model, you greatly reduce validation cost. You also greatly improve the schedule, and it also improves validation test automation. So a lot of benefits. It's really about the one system of record. And ultimately, this should generate other systems of record. Yeah, if there's many, many systems of record, that doesn't mean much. They're not a system of record. So if you really want to stress your development, you take these autonomic agents that get developed for IoT, and you actually have hostile attacks on them. So in our extreme dev environment, we actually call this the red deity for adversary, and we make sure that it is much more flexible and much more resourced, and it has all the insights of the trade-offs the agent has made. So take the example in green there, where you have cloud analytics to drive a car. But the learnings have to be compressed to fit in a car's constrained battery, constrained runtime. And the red deity knows the limitations, the gap, if you will, between perfect God mode in the cloud and the limitation that runs inside a constrained vehicle. And so the red deity attacks that. Same thing with other models on the left, not analytics, but the actual SysML modeling in advance. And the perfect model has quite a debug gap when you validate the entire system, the functional simulator, or the implementation of FPGA. You always know the gap between ideal and what actually got validated in the IoT environment. In the factory, the hospital, whatever your site or IoT solution is. And red deity is both a platform attack as well as a network attack. So when you validate things, having these extreme environments are quite helpful. So we'll set some reminders, and then we're going to show how to actually implement here. So we want to remind folks that find an initial SysML project, some mentors, and I'll describe that in just a minute. Also, that architects and developers should be measured on what they don't throw away. What are they building that formally scales, that is always complete and correct? Think skyscrapers, not 50 Amish barns that are stacked up. Stacking up barns is an art. It's not engineering. Engineering is when you can continually double the skyscraper number, the height, the weight. If you can keep doubling, that's engineering. If you can't scale, it's an art. IoT is all about engineering and scaling. How do you auto-generate? All systems of record, all APIs. How do you put namespaces around wrappers so that you know that this namespace means HIPAA compliant, RoHS compliant? So for more information, here is the most popular book on SysML. And it gives many examples there of object-oriented developing cars and IoT devices, how to write use cases, the INCOSE document that actually defined the original systems engineering. It's in paper, and tools automate that. And then the SysML language here, the best book on the subject, highly recommend that book, 3rd edition. And then the link below that is 500 slides that go with the book. They use the same tool, the same process, the same language that we're showing today. Also, there's a great ebook out there that is an IoT device in 70 pages. A little ebook, 70 pages. It auto-generates from your example the actual code for the software and the code for the hardware. So you actually build an IoT device in SysML in 70 pages. And then at the bottom here, more information about the product there. We highly recommend floating licenses. 10 people's got enough for 100 users. We'll describe that in a minute. If you want videos to learn this, if you've got partners that require open source, they'll work with a more constrained non-commercial product. Model I/O is interesting, and you can do XML import back and forth between the commercial product and the open source product. We still recommend that more advanced development uses the commercial product, but it's nice to know that for your partners, students, and others, you can translate. What is system engineering? That's the definition. That's the handbook. And where can you get the best cost insights into all development? The USC does all the studies. That's where all my graphs came from earlier, and I gave them credit for that. Let me go back to the main graph we showed in the first hour. The main graph of cost here is that heavy methods like NASA, number 2, are $1,000 per line. Light methods like Agile are more expensive. So number 1 in the top left, if you lose your factory plane medical, that's extremely expensive. So number 3 is model-based, always complete and correct, doesn't have the complexity of UML or paper or lots of systems of record keeping them in sync with each other, but having one authoritative that is auto-generating all of your initial templates and code. So all this document is downloadable. Just reminding you that we have all the acronyms here that will help you as you understand this. So let's go through an example of building out a lab. How would you learn SysML? Ideal would be to have a current project, groups of 2 or more people, some mentors, and it's nice to have your reference cards ready, your book, the .zip file we had you download, pre-install the software, which I'll show on the next slide. And when we teach it internally, we have 5 labs. Here's a glossary to build out a domain model, and you use that immediately with requirements and even more detail. Every one of these labs generates a useful report of a useful product. So nothing here is throwaway. This is actually accelerating one of your products. And the 5th step actually generates the template code and the template test cases. And all of this uses the well-known book and the well-known zip file that we just pointed to earlier. So how do you install? There's the link. It works best on Chrome. It's that product's name. It's what they say. And so you follow the instructions here. Free trial for 30 days. If you need more, here's the link to get an extension. In the lower right, remind folks to install System Engineering version because that has SysML. The other versions do not. So go with the System Engineering version. And we remind folks to get the seat licenses. 10 seat licenses is probably good for 100 developers. Example of some of these labs, an example of SysML, we use the expression RSVP. So requirements, start with requirements. Build out your structure, the what. The V is the variable behavior. Start documenting these. Typically, you've got 3 kinds of SysML flows. And then finally, add your parametric requirements. Notice the ports are connected. That's the whole key of SysML, are these connecting ports. That is what's going to generate the complete and correct reports. That is ultimately what's going to be your object-oriented relations and even aspect-oriented after that. So here's a lab of generating a domain model. Because this is the first lab, it's the simplest. It has no dependencies. And this actually becomes your project glossary. So the very first process is to generate a glossary. So this isn't going to add the GUI. It's not going to add all the quality abilities. That comes later. But to say these is the first set of objects and their functional relationships between them. And multiple tips from object-oriented. And you quickly get to about an 80% sufficient. And we do this anywhere from 1 day to half a day. We have use cases driving everything. What is a use case? How do we have teams organized to do this together? Notice that all of our use cases, it's about the data driving IoT. So how can you design your use cases for machine-to-machine data? So here's multiple tips there. We think of a model view controller, MVC, and how is that done? How do you write effective use cases? The challenge here is that a lot of books out there, they're very good, but they still have a lot of human, whereas machine to machine, the user is the data, it's the machine. And if you think of data being 100 times more common and popular than human, you have to slightly transfer most of the books out there. So another lab is to incorporate all of the requirements, and that's the second of 5 labs. And here's the techniques there, how to actually use active verbs and document all of that. Again, it's still about the data, not the functions. That's why we talk about things like object-oriented, aspect-oriented, not things like functional programming. The third lab is getting into the flows. And so here's a sequence diagram. And so when to use it, how to use it, some useful steps there. So to know when to use this kind of a flow instead of an activity diagram or a state transition machine diagram. Those are the 3 main flow diagrams. There's more in the slide notes, which you can download. How do you do this? Well, step 1, start from outermost flow, go to innermost flow, and you first complete the ports. Every time you have a single entry, single exit, that's a great candidate for a port. And then for each attestation type, if you have you're testing, you're actually reporting on latency or spatial or environmental. For each type, you do the same kind of outer to inner. And you attach the ports. And you add all the requirements. You add all of the KPIs. How to get certified. This is basically the measure of productivity of an IoT developer. And so here's the 4 levels of certification. OMG is the standard. It's the same standards body that creates the DDS, the only secure data transport. the same standards body that creates IIC, the Industrial Internet of Things Consortium. So it's a very cooperative group there, and to get professional certification. So let me go back here. So reminder here is that the goal, the problem of IoT is the biggest study ever shows that only 3.5% of faults are detected in the development cycle. How do we detect at least 80% and get that closer to 100% as early as possible? Because with IoT, these faults now impact the motors, the cars, the planes. So that's going to be key. That's the motivation and the problem. And if it costs 1x to remove them early, notice how much it costs to remove them later. And my argument in the lower right is that it really costs 100 times as much in IoT. These numbers are pre-IoT. Removal now is much more expensive because now you have to redesign all of the cross dependencies and keep in sync with the digital twin of a changing physical world. Keep in sync with regulatory. So if there's not these modular dependency of the physical twin, it's quite challenging. A car has a high-def map of the real world. From that, if your development environment is very similar to that, you can easily add additional validation, reports, verification of features. And without that high-def map in production and in development environment, quality means nothing. And there's no predictability about the costs of bug removal or even how regulatory compliant are you. I mean, these numbers are staggeringly expensive, and this is pre-IoT. So these removal and late introduction of faults and all these problems will get worse with IoT. So again, the benefits of a single system of record for all blocks, all flows, all requirements. If you have less than this, how do you know the car is safe? The factory is optimized for things. How do you know that medical devices are compliant? The drone, the robot, the robotic arms won't hit each other in timing? How do you have any assurances if you don't have a common model and common development environment? On slide 6 here, let's go into more detail about traditional development on the left and then IoT specific development. On the left, this is an informal art. There's no guarantee of doubling requirements. There's no guarantee that an error can't be reintroduced. A product that used to be functionally safe is no longer safe. The latency is bad and the airbag doesn't go off soon enough. Something got introduced and the encryption is weaker. On the right is formally complete and correct and future-proof math that is sufficient for driverless factory, driverless retail, everything. On the left, internet was just API syntax. This is no better than a car parts store and know that the parts fit together. On the right is driverless semantics. The car actually has safety regulatory compliance, semantics. It's part of a bigger ontology that verifies these semantics and quality. On the left is 3 nines uptime. There's still shared memory, shared resources, shared languages like Java. On the right is 9 nines uptime. The left only has to worry about surface area. The right has to worry about the network, the actuating motors, compliances. The left is a human browser of read-only of mostly audio-video types. The right is data driving, data getting controlled, and being autonomic. So we focused on the development in the first hour, and we focused on validation in this hour, the two blue lines at the bottom, but both quite a change and quite a step forward from pre-IoT development. So we covered the benefit. Now we're going to look at the actual diagrams. SysML is behavioral flows and its structural blocks. What's different about SysML is you can actually add requirements and parametric constraints, the KPIs, directly to the subblocks and flows. And with port connectors, you can guarantee those properties are true from end to end, that nobody broke the build. So at every check-in of the paper models, of the SysML Tools models, you can guarantee that you kept the functional safety. SysML is much better than UML for this because it adds these requirements and parametrics. It adds these chains of ports to guarantee end-to-end compliance. It also adds hardware. You can't do that in UML. UML only models software. So to be able to take and say that you can model hardware, power, flows, and anything that hardware physically can do. It also auto-generates the APIs and unit tests. Very useful to initiate. It auto-generates from the ports all attestation. So you can know assurance that this is compliant, and you can require that of partners. So how do you know that their car is safe and that this part for airplane medical is safe or compliant? The history is from the same object-oriented. The challenge is that all of these became into UML as a committee and became the union of them. UML2 cleaned that up a little bit, but SysML is the same subset. Everything there is orthogonal. There's only one way to do it. It also took in INCOSE. As it says at the bottom, that was the foundation for system engineering. So all paper deliverables of system engineering are defined by that. And those are the two inputs that create SysML that's part of omg.org. Here are some interesting tools that we showed how to install and use. There's also the Model I/O that's free. As it says at the very bottom, floating licenses, probably 10 licenses for 100 senior developers is sufficient. So we showed how to build future-proof, which is not an easy problem, how to build future-proof processes and the how. And this last part is the what. That if data is driving the car, data is really driving everything. That's the disruption to IoT. And in the second row, we show where data-driven replaces internet. So TCP/IP as we know it in the far right, that's the leading research that shows the benefits of data driving. Let me go back a slide. So currently, data is not a first-class citizen. Random historical tight coupling, instead of data being the earliest thing that is captured, packaged, named, owned, managed, we have all these other tight couplings. Many IP addresses, many names, many certificates to files and blobs. There's many things where data is not first class to drive. There's also many random boundaries out there. So when you think of fault tolerance and quality, it's not around the isolated data and its dependencies. It's really around random things of software and hardware, vendors and history, versions. That's why nothing is better than 3 nines uptime, except for Erlang and OTP. They're data graph, data-driven, 9 nines uptime. The best data centers are 3 nines uptime, which is still 51 minutes a year of outage. Not good for IoT. Even compute is tied to data movement. Every time you move data across a compute, even if it's only moving 10 nanometers, that affects your power, latency. That's the surface area you have to have for fault tolerance and security. So the more you can shrink that, there's many benefits. So that's why long-term, you really want to build your development and validation around the data today and have good processes today, and know that ultimately the data owners and the data will drive everything. Even replacing typical compute as we know it today. So here's 4 generations of computers. Think of Moore's law as the density of the speed of light. How much can we keep shrinking the density, the distance of the speed of light? And you can think of that as 4 microarchitecture generations, an entire die, and then multi-core, where it only has to be in its individual core, with 100x improvement in size and therefore performance. A 3rd generation is hetero, where you can have these very small transistor types like tensor processors, much, much smaller die space than, say, GPU or FPGA, much more parallelism because there's so many and they're so small. And 4th generation would be data-driven, data graph-driven, that guarantees the minimum data movement. So this is very different than the generations above that effectively move the data to the compute. This is guaranteeing the minimal movement of data, and it's more like moving the compute to the data. Huge improvement in power, latency, surface area for IoT security. So data-driven is huge. The networking here on the left is a traditional TCP/IP stack. Data second class. Where is it? How's it being routed? How's it being grouped? How's it being muxed at every traffic point? Pretty random. On the right is named data network. And earlier we showed the leading research where it will replace DANE, DNS, TCP/IP for many quality data areas. This is where data gets captured, owned, published. Very different than the randomness out there today. How do you group, route semantically today? How would you dynamically update it for a specific aspect oriented? Another example of data oriented, I gave the example, this is open source, dpdk.org, the data plane development kit. This is used by all switches, all major IoT gateways to get 2 to 50 times more throughput. How does it work? There are no interrupts, no blocking, no copies, no ring transfers, like from ring 3 down to ring 0. It's like direct memory access. When you develop to this, data is first class. The data packets, not the platform. So you can use off the shelf from multiple vendors. So, all major hardware vendors have solutions in this space. All major networking and package use this for off-the-shelf parts. But notice all the benefits that you get when data is first class. So just to repeat that, at the bottom, remove all legacy tight coupling that limits data's freedom. Only machine actionable data drives everything. So going back to our agenda, we've been showing that IoT is an OT control network of machine actionable data. Focus on the control plane and the data plane. How do you do that? Model-based, one model, one process. In the short term, it's object-oriented. Aspect-oriented is a sufficient superset. SysML language and the EA tool we showed with labs how to develop to it. One hub, and then really long-term, data drives everything and replaces internet, computers, AI, human contract, everything. Any questions, put them on the text. For follow-up, you have my name. Feel free to email me. You have the presentation at the top. I actually have very large white papers about this, and I'm writing a book in this area. So the book is Data Drives, IoT Data Drives Everything, all business value. We've covered this from a variety of angles. If you didn't see this, this is the generations of data. So data, IoT data is currency. Don't give it away. If you give away your DNA and other data about yourself, that's money. So here's the phases. Pre-IoT was phase 0, embedded. And there's an example on the right of smart parking. So in the lowest right, you only know if it's empty or full. Once you add internet, phase 1, you now know the entire history and the entire parking spots. Once you add OT, you really are getting into a control network and semantics and end-to-end data, so you can start answering who, what, when, where. Phase 3 is that it's all correlated. You mature the data, you get to monetize it more. There's more value as you have more mature data. And remember that all business value is IoT data. All business value. So in phase 3 there, it's actually correlated data that you can buy, sell with others, that you can do AI learning on because it's all correlated. All the hardware is correlated. It's exposed as software semantics, software defined. Everything's contracted, rule of law, central software defined. So now I can answer even more why and how questions. Phase 4 is prepare for that, because that's when things are data graph driven and the AI does more and more abstract adaptation, replacing a lot of things that are limiting data today. If data is going to drive, what's limiting it? So we covered a lot of things that all fit with the theme of how to do future-proof, composable, semantics, and quality. So thank you for your time. Any other questions, feel free to follow up. And hopefully this is useful to you, and you have the links where you can download this. And thank you for your patience. Thank you for your time.